Yeah, so thanks everyone for joining in this third session for Dive into Deep Learning. This is our third coding session, which is on recurrent neural networks. So yeah, so let's begin. What are sequential inputs? So sequential inputs are the inputs in which the data is basically provided sequentially. And what I mean by that is that it's ordered temporally. So like the order of the data in which it's coming in also matters. So for a sequence, we respect the temporal ordering of the data. This is especially true if we are working with language or language text, basically in any language, because the order of the words itself decide the meaning of the sentences, and any random order of the words or any random order of the characters do not necessarily make sense. So sequence model require specialized statistical tools for estimation, like autoregressive models and latent variable autoregressive models. Autoregressive models basically are just the models which use some of the previous values of the inputs to predict the next value. And then using that predicted value, they just make a prediction on top of that. So for example, I can use the values of inputs. So here X are inputs. I use the values of inputs from first input to t-1 input to predict the probability of the next word or the next character. And then I can combine those, do it for the whole sequence to generate a combined probability. This can be done either by using a lot of different words preceding the word I want to predict. So for example, I have a statement with 4 words. I can use those 4 words to predict the 5th word, or I can encode the information of those 4 words into a latent variable or a hidden state, and then use that hidden state along with my input to generate the 5th word. So the second approach is called this latent variable autoregressive model, which is also shown in this flow diagram here. You have some input, and that input, that input along with the hidden state gives you a new hidden state, which helps you predict the output. So in this case, you don't necessarily have to save all the preceding inputs because you're updating your hidden state every time you get a new input. So we'll talk much more about it in the upcoming slides. And this is just another example. Here, this blue curve, the top blue curve shows the input. And what we are trying to do is we are just trying to read in a few preceding values of the input and trying to predict the next steps. So for example, I use 4 previous values and try to predict 1 step ahead. Then that gives me the blue curve shown in the bottom, which looks pretty good. But let's say I use the 4 previous values and try to predict 4 values ahead of the current value. Then the error starts accumulating, right? Because I use the 4 values to predict the 5th value, and then I use that 5th value itself to predict the 6th value. And that 5th value might in itself have an error. So my error keeps on accumulating the further out I want to predict. So as you can see in this 4-step prediction, the prediction is starting to deviate a little bit from the actual input. And if I start predicting 16 steps ahead or 64 steps ahead, my prediction starts to deviate much more because the errors keep on accumulating the farther out I try to predict. So this was one limitation of these kinds of autoregressive models. In the case of text inputs like the language inputs or letters or characters, we have to do some pre-processing because text typically is human readable. But it's not necessarily machine readable. We have to convert it into a machine readable format to pass it into our algorithms or to pass it into our deep learning based or neural network systems. So this is one example wherein the input is some text from the time machine by HGULs. So these are some 2 lines from that text. This is completely human readable, right? Because we read these languages. But then to convert it into a machine readable format, we follow these 2 steps, wherein we firstly tokenize all these words or all these characters. So we have separated all these individual characters by this space. And so we have identified all the different characters and all the different words. Then using these different unique tokens, we form a dictionary which contains all their frequencies. And using that, we make a vocabulary. So basically each unique token in our data or each unique token we found here would be assigned an index. So the occurs most number of times. So we assigned it an index of 1. Then I occurs the next most frequently, then we assigned it an index of 2, and so on. So each unique token which we found in our data is assigned a unique index. This is what we call a vocabulary. So starting from the text, you tokenize everything, you identify each individual words. Each individual word is then assigned an index, which is just a number. And you do this for all the unique words or all the unique tokens in your data. And then we just, for each statement, we can convert each token now to an index. So now we have an index for we have an index for time, we have an index for machine. So now instead of these statements, which were written in any particular language, we can convert it into numbers, which are machine readable now. This is one way of converting, of pre-processing the text to make it machine readable. Other ways can be what is called one-hot encoding, wherein you have, let's say, 4 different unique inputs, and you make a vector of length 4 for each input. You will just say 1 at one particular unique index. So for example, we had these 4 inputs and we made a vector of length 4, and then each vector represents a unique position of the value 1, and that represents the vector encoding or the vector representation of a particular word. So this is another way. This is a third way. Again, you had a statement, you convert it into tokens, and then you just, due to some using some transformation or an algorithm, you converted those individual tokens into vectors, which are machine readable. So then we talk about language modeling. Language modeling is what I've been talking about so far, is the task of predicting the word or what word comes next given a sequence of words. So computing the probability distribution of the next word given a sequence of words. So for example, we had all these x's, which are in our vocabulary. We had a sequence of x's starting from this first index till this index t, and we want to predict the probability of a particular word at the index t plus 1. So this is what we call language modeling. And all of these words, all of these x's are individual words, or it could be individual characters, which are all there in our vocabulary. So we do encounter language modeling scenarios all the time. For example, when we start typing something on Google, it predicts what should come next based on what we have written. So for example, what is and then you could have different ways of finishing that sentence. So it predicts those, which is basically predicting the 4th word given the 3 words. And then when we type something on our phones, or the autocomplete feature, and then all those things also predict what should happen next based on the words which we have seen, which it has seen previously. We do encounter language modeling in different scenarios in our everyday lives. Then there is this thing called n-gram language model. So the idea here is that it's not always possible to use all the preceding words to estimate to predict the next word, right? Because the sentences can be really long. So for example, this sentence can be really, really long. It can have 10 words, it can have 20 words, it can have 10 sentences. So we define the scope of the previous words we will use to predict the next word. This is sort of called as the n-gram language model, where n-gram is just a chunk of n consecutive words. So like unigram can be one individual word, like the, or students, or opened. Then bigrams are pair of 2 consecutive words. So it's not just pair of any randomly occurring word, it's the pair of consecutive words in our data. So like these students, or students opened, or opened there. And then trigrams are just triplets, and then so on. So then we basically do the assumption, or we assume that our t plus 1th occurrence of the word depends only on the previous n minus 1 words. So for example, if we are learning a 4-gram language model, then, and we had this whole statement, then we'll discard everything before these last 3 words, and then we'll only use these last 3 words to predict the 4th word, because we are doing a 4-gram language model. So we'll only use students opened there to predict this 4th word, and we'll not use this previous part of the sentence, because we are just defining a 4-gram language model here. And how we will write it? So the other way of writing it actually is that probability of a particular word, given that we had students opened there in the previous, as the preceding 3 words, would be given as the number of occurrences of this phrase, which is students opened there with a particular word, divided by the total number of occurrences of students opened there. So just to take an example, let's say we have our database is a whole book about schools, right? And there we are trying to calculate this probability. So this W can be anything. It can be it can be bag, it can be books, it can be cars. So it could be what are the number of cases in which we found this phrase students opened their book, and then what are the total number of cases in which we found this phrase students opened there. So just the ratio of these will give us the probability of that particular word book occurring after these three words. So that actually that is a good segue to talk about the problem which I was just about to discuss, which is the sparsity problem, which is that long sequences occur very rarely in our data. So let's see what that means. So if we are only talking about unigrams, for example, the, and, of, then they might, and these are just the counts in that book we were talking about, The Time Machine by G. Wells. So these are the number of occurrences of these unigrams. Then we talk about bigrams, and then these are the number of occurrences of those bigrams. But then we move on to even longer sequences, and then their frequency starts to decrease, right? This trigram, which is the time traveler, which is supposed to be very, very frequent in the book about time machines, is only present, occurred only 59 times. And as you go to longer and longer sequences, the frequency with which any particular long sequence occurred decreases by a lot. So this creates a problem, right? So for example, we wanted to calculate this probability. What if this phrase students opened there never actually occurred in our data? Then we would not have any number here, and we would not have any number on the denominator itself. So we would not be able to calculate this probability just because that phrase did not actually occur in our data set, or it occurred only once. Let's say the phrase students opened their book is the only phrase that occurred in our data. Then these two would be one, and we just don't have enough information, or we just don't have enough examples to, confidently predict what the probability should be of some other word. For example, students opened their bag or students opened their car, because that just didn't occur in our data. So that's why we modified the problem a little bit. So instead of using the t-1 or some number of previous occurrences of words, we use a latent variable. So this is what we had defined the problem previously: probability of a word at a particular time step t based on the words present previously. We, instead of using that, we encode all that information into what we call a hidden state. So now we just we modify the problem a little bit and frame it such that what is the probability of a particular word xt given the hidden state at time t-1. So we have a hidden state at time t-1, and we use it to calculate the probability of a word at time t. This gives us a new hidden state, which we can then use to predict the probability of the word at t+1. So this is again shown by this flow diagram here. We had some input at time t-1, and we had a hidden state also, which came in at t-1. Using this, we predicted, made this hidden state, which is at time t, and predicted what the probability of word at time t should be. Then this hidden state at time t would go on to predict, to help us predict what the probability of a word at t+1 should be. So instead of using the sequence of words itself, we have encoded them somehow into a latent variable called hidden state, or a hidden state, and we use the hidden state along with our input to make the predictions. So yeah, so let's so now that we have a framework, let's think about how we will do it in the case of a neural network. But let's begin with a neural network without any hidden state. So this is just the multi-layer perceptron, which we talked about in the first session. So we have some inputs, we have a hidden layer, and then we have an output. So there are some input nodes, hidden nodes, and then output nodes. And this is how the equation on the right is how we typically write this. X is the input vector, WXH is the weight vector or the weight matrix, which maps the input to the hidden layer, and BH is the bias. This phi is just the activation function, which could be any nonlinear function we've talked about. And then this H is again multiplied with a different weight matrix, which maps the hidden layer to an output after adding a bias term. So this is how we basically encoded or understood the multi-layer perceptron. And I just wanted to bring this up because RNNs are also going to be very, very similar to this. And it's just going to be just going to be a small extension of this equation, wherein we will have a hidden layer coming in from a previous state as well. So so just keep this equation in mind, and then let's look at what the RNNs are, which actually have a hidden state. So the RNN architecture can look something similar to this. So let's just focus on this first node on the left side. We have some block which has an input, which is an x t minus 1. So this is an input from time t minus 1, and a hidden state which is coming in from the previous step. Both of these are multiplied to some weights, on which an activation function is applied, and that gives us an output and a new hidden state. So this is somewhat similar to what I was just talking about. You have some input, you multiply a weight to it, apply an activation function, and that gives you a hidden layer. That hidden layer is multiplied to a weight, and that gives you an output. So the only modification here is that instead of just the weights which are modifying the input, we have the information about the hidden layer at a previous time step. So this time sequencing was not there when we were talking about multi-layer perceptrons, but now this is the new thing which we have. So yeah, so the main thing I want to emphasize here is that as compared to the multi-layer perceptron, where we have weights multiplied to input x, here we have weights which are also multiplied to the hidden state at the time t minus 1. So I have an input at time t, and I have a hidden state at time t minus 1. Both of those combined, multiplied by weights, form the hidden state at time t, which then again similarly forms the output at time t. So we can represent the neural network, we can represent an RNN in this form as well. And if you look up different blogs or different papers, this is how people typically write, form or show RNNs as well, wherein you have some input, which goes into some structure of a neural network, which gives output as HT. So input gives a hidden output or hidden state as output. But then that hidden state again goes back inside the same input, again inside the same network, and gives you another output at t plus 1, goes back again, gives another output at t plus 2, and so on. So what this means is that the weights which we are using here, so weight which maps input to the hidden and hidden to the hidden layer, are shared between different states. So the network is just this one thing which has the weights. These weights are shared across different hidden states. So that's an important point to note here. And these different hidden states are temporal states. So I had a state at t minus 1, then I had a state at t, then I had a state at t plus 1. So these are different temporal states. And we can show this representation in this flattened manner as well, which is called unfolded RNN, wherein I'm showing the individual things separately, although all of these are just the same network with the same weights which are shared. So I have some input at time t equal to 0 that goes into this, which multiplies by the weights, applies an activation function, gives me a hidden state at t equal to 0. This hidden state is passed on to the next time step. It uses h0 and x1 to form h1. It uses h1 and x2 to form h2, and so on. So this is the main idea of a recurrent neural network, which is a bit different than what we have been used to thinking for convolutional neural networks. This is just another example for character level predictions. So it takes in one character as an input, it uses the hidden state, and it gives an output. So let's say it took an input of M and it gave an output A. Then this hidden layer which was formed will again go into the next step, and it will take the next input, which was A, and then give me the next output. This next input will again use the hidden layer of the previous step and give me the next output, and so on. So let's just look at how we train an RNN, and then let's take a pause and then go over the questions. So this is another way of representing the RNN. Here I'm doing the predictions on words. So I have the word D, students opened their exams. These are X1, X2, X3, X4. Like I was talking, we pre-process them or encode them to make them into a vector. So this first pink step is basically encoding these words into a vector. This is the input which is passed onto my neural network, which is shown here by red. So let's say we are giving this first word as input. So x1 is going as input here. It's going to use this x1 along with h at time t equal to 0 as both of the inputs, and it's going to predict some word output. So this y hat is the prediction which this network gave at time t equal to 1. I compared this y with the next word it was supposed to predict. So because this network is supposed to predict the next word, this y hat would be compared with students. And we will compare those two words and create a loss, like we typically do, right? Because we wanted this word to be students, we'll compare what this actually is and generate a loss or calculate a loss. Then we'll move on to the next step where we gave it students as the input because that's supposed to be our input, and see what it gave as an output and compared it to the third word, which is opened. So we compared y hat 2 with opened and generate another loss. We'll do that for the whole sequence. So we get a bunch of losses, we sum them together, or we take the mean of all the losses across all time steps, and that gives us the cumulative loss. Okay, so yeah, so I'll just quickly go over this again. So we have some input at time t that is encoded. It uses the hidden state at time t minus 1. It gives a prediction. We compare that prediction with the input at time t plus 1. So we compare y hat 2 with respect to x3, calculate the loss. We do that for the whole sequence, get an average loss. So now that we have an average loss, we want to do the backpropagation like we did, right? So we calculate the gradient of the loss with respect to the weight, and then we update the weights. That's how we've been doing backprop in the previous two sessions. That's what backprop is, right? So this is the weight which we calculated. This is the loss which we calculated, j theta, which is the average of all the losses at different time steps. And then I want to take the derivative or the partial derivative of this with respect to the weight. But this would actually depend on partial derivative of the loss with respect to all the weights at all the different time steps. This is because if we look at jt depends on the output, right? So jt depends on whatever the output was, because output was the prediction minus the ground truth. So jt depends on output, and output, if we look at this equation on bottom left, depends on the hidden state. So jt depends on output, which depends on the hidden state at time t. Hidden state at time t itself depends on the weights, and it depends on the hidden state at time t minus 1. But the problem is the hidden state at time t minus 1 itself depends on those same weights. This is something new which was not happening in CNNs. Here, these weights, WHH, are shared for all these hidden states at different times. So a hidden state at time t depends on hidden state at time t minus 1 and the weights, but the hidden state at time t minus 1 itself depends on these weights, and it would depend on the hidden state at time t minus 2. So to calculate this gradient, we need to calculate all these different gradients and apply the chain rule so basically we need to apply chain rule to estimate to do the gradient, to do the total gradient of hidden state at time t with respect to the weights, and propagate it till the first time instant. So this is how it would look like. Let's say I want to calculate this loss at time at step number 3 with respect to the derivative of the loss at step 3 with respect to the weights. And again, as I said, weights are shared. So all of these WHs are same throughout, and they are shared across all the different time steps. So the first thing would be I take the derivative of the loss with respect to the output, then the derivative of the output with respect to the immediate hidden state. So derivative of the output with respect to the immediate hidden state. But then I also need to take the derivative of the hidden state with respect to all the previous hidden states, and the derivative of the hidden states with respect to the weights. Does that make sense? And the final step in this is that this derivative of the hidden state at time 3 or step 3 with respect to some other hidden state at other time steps itself is a chain rule. So del h over del h3 over del h1 would itself be del h3 over del h2 and del h2 over del h1. So So it's basically a chain rule. So sum of all of these different weights, and for each case, for each combination of these derivatives, we need to apply the chain rule to calculate the total derivative. So if I want to calculate the derivative, calculate the gradients at a particular time step, I have to propagate it throughout till the first time step and keep on multiplying all of these different gradients. And this is because the weights W are shared across all the time steps. So this creates an issue because computing the gradients, there are two issues primarily. Computing the gradients across the entire data set would be very expensive because my entire data set could have hundreds of sentences or multiple sentences. And for each step, for example, step number 101, I'll have to propagate it to step number 0 or time step at time equal to 0 to calculate the total gradient at 101. And then I have to do that for 102, and then I have to add up all those gradients to compute the total gradient. So practically, we compute the loss only for a batch of sentences. And this is what is called truncated backpropagation through time. So for example, we do not propagate this time, the gradients from this particular time at t till 0. We only decide a chunk or a window. So we'll say that we'll only propagate it till let's say 20 samples or 5 samples or 4 samples or 4 sequence words, and we just calculate the we just propagate the backprop till here and calculate it here, and then move on to the next chunk, do it, move on to the next chunk, propagate it in the back like this. So this makes it this is sort of a solution because in the case of RNNs, you'll have to propagate the gradients throughout the whole sample otherwise. But then again, we do have those two problems which were earlier discussed, the problem of vanishing gradients and the problem of exploding gradients. So as I earlier discussed, for each step, you need to multiply it with all the different gradients in the previous steps. And if any individual gradient is small, the product would keep on getting smaller and smaller, such that a gradient from a faraway step would just be lost. So there is a bit, let's just take this example and see what that does. So for example, we have this statement, the writer of the books, and then we have to predict the next word. Let's say the next word could be is or are, right? So if our algorithm, if our neural network is working based on the syntactic recency, then it would use writer as, and then it would know that this next word depends on the writer and would predict is. So the writer of the books is. But if we are in the problem of vanishing gradients, then it's not able to look back that much, because by the time it starts getting the gradients from the very early steps, the gradients are very small, so they don't make a difference. So it will only use the very nearby words to make the prediction, and it would make the prediction as R, because it's only using books, and it's not able to use writer to make the prediction, which is incorrect. So that's what the vanishing gradients would do. The words which are far away from the prediction step would not actually make a bigger difference, because the gradients have kept on getting smaller and smaller and smaller as they were propagated. And then the next problem is exploding gradient, which is if the gradients are greater than 1 and we keep on successively multiplying them, then they can very easily explode. So to limit that, we use gradient clipping, which is basically we set a threshold value, and if the value of the gradient exceeds the threshold value, we just clip it to that value, as shown in this plot. As shown in this plot. So again, this is just a quick representation. The gradient here is very high. So if you do not apply any clipping, then it will modify the weights to a very large, by a very large number. But if you apply gradient clipping, that it would modify it by a smaller number. So that would prevent this problem of exploding gradients. So before we talk about advanced RNNs, we can take another pause and take some questions, if there are any.
Yep, so this one, so the question is, so the truncated backpropagation is implemented, is it implemented using a hyperparameter or using the effect of vanishing gradient? You can just truncate dynamically in each backprop.
I think it's just, while the training loop is going, before the training loop is decided, I think that just the width of this truncation or the size of the chunk on which backprop would be done is just decided, and then that is used for training. So I don't think it's a variable parameter. I think it's just decided that, hey, this we will use this as the size of truncation or this as the size of our chunk, and then that's what the training is done on, or backprop is done on. So yeah, let's talk about some advanced RNNs as well. So like I discussed, this problem of vanishing gradients and the problem of exploding gradients. We can solve the problem of exploding gradients by gradient clipping, but I did not discuss how we solve the problem of vanishing gradients. It's typically discussed by changing the architecture of your RNN itself. So by using these gated recurrent units or LSTM. So let's talk about these. So gated recurrent units introduce this architecture itself introduces the mechanism to control when the hidden state is updated. So earlier in our RNN, the hidden state was always updated at the next time step, right? But GRUs can actually decide when the hidden state is updated or how the hidden state is updated. It does that by introducing two gates, like the logic gates we have. One is called the reset gate, and the other one is called the update gate. The functional form of this, how it's calculated, is very similar to how we were calculating our hidden layer. So you just have the input and the hidden state at previous time step going through an activation multiplied by some weights, and you get the reset gate and update gate. The only difference is we are using the sigmoid activation. So the values in RT and ZT would be either zeros or ones. So again, RT and ZT are again vectors, and they would have just zeros and ones in them. But the idea is exactly the same. The equation is exactly the same in which RT and ZT values are computed. After this is done, we modify the hidden state using the output of the reset gate. So if we look at this equation, the output of the reset gate RT and the previous hidden state, we take an element-wise product of these, and we feed that into the function which generates the new hidden state. So if we just ignore this part and we consider this part as ht minus 1, then this is the exact same equation we were using in our conventional RNNs. An input, a hidden state, both multiplied by weights, apply an activation function, get a hidden state out. The only modification in this, in GRU, is that instead of just multiplying the hidden state with the weights, we modify the hidden state by this reset gate, and then calculate the calculate the new hidden state. So yeah, I've written here, this was the original one. Here we have modified ht minus 1 by introducing this reset gate. And this reset gate decides which elements or which states of this ht minus 1 would actually, or which elements of this ht minus 1 would actually be influencing ht. Because RT, and this is an element-wise product, and wherever RT value is 0, those corresponding indexes of ht minus 1 would not make any difference in computing ht. While wherever RT is 1, all those values of ht minus 1 will be passed to ht. So RT is the reset gate, which decides which values of ht minus 1 will actually be used in computing ht. And then we have the update gate. So update gate decides how much of a new hidden state is used. So let's see what I mean by that. So if we follow this path, we calculate this after this tan h, we calculate a candidate hidden state, right? This is what I was showing in the previous slide. So this is my candidate hidden state or my new hidden state. After we use the output of the update gate to decide how much the new hidden state will be used and how much the previous hidden state will be used. So there are two small things here. One is the reset gate decides how much previous hidden state would influence the new hidden state, and the update gate decides how much the new hidden state will be used. So in this mechanism, GRUs are able to control whether a particular input is actually useful or not. So for example, if we give it an input and the reset gate is all 0, right? Then the reset gate is all 0. ht minus 1 would not influence at all in updating ht. So the ht I will get would not be influenced by ht minus 1 at all. And so this previous hidden state is not useful in this step. So based on the weights and based on the training process, RT itself had some weights, and it can just learn that, hey, the previous hidden states are not useful for me, so I will not use them. Or the previous hidden states are useful, so I will just say that all my RT values are 1, and that gives me the conventional RNN to get the new hidden state. Same with the update gate. If my update gate values are 0, so this would be 0, this would be 0, it would be the conventional RNN now. But if the update gate values are 1, then it would just pass the previous hidden state to the next state. Just in the meantime, I can maybe go over the things again. So reset gate decides how the previous hidden state will influence the new hidden state. And update gate decides how much of the new hidden state will actually be used to create the final hidden state. That's the basic idea. And then the equations which we are using are very similar to the one we were using for RNNs, the typical RNNs. Let's move on to LSTM, which are similar to GRUs, but a bit more, and they contain a bit more gates and some more new things. So yeah, so LSTM, again, the unit is again similar. The input is the, again, input. The two inputs are, one is the actual input which you give. The other input is the hidden state from the previous time step. And LSTMs have these three different gates and a memory, or it introduces something which is called a candidate memory. So up till now, you can consider LSTM as a unit which saves a value or saves a memory in itself. So it would have a hidden state, it would get an input, but it also is able to save this memory or keep the memory of important stuff, which it saw in the previous time steps. And then it has these different gates to manipulate or generate this memory to predict or to make a new hidden state. So let's look at those things one by one. So let's only focus on the forget gate. So as I said, there are three gates. One is the forget gate, other is the input gate, and the third one is the output gate. So let's look at each thing and see what it's doing. So let's just focus on the forget gate for now. So forget gate decides how much of the candidate memory is going to be used, or how much of the candidate memory is going to be to forget, basically. So like I said, LSTM saves a candidate memory. So so we would have an input at time t, we would have a hidden state at time t-1, but we would also have a candidate memory at t-1. So these are the three things which are feeding into an LSTM block. Forget gate decides how much of this memory is to be forgotten, or how much of that is to be passed to be used to make the time to memory at time t, yeah. And then let's see how this candidate memory is made in itself. So this is the step which makes the candidate memory. It takes in the input and the hidden state. It applies a tanh activation, and that's how this temporary candidate memory is made. So this is the step where this candidate memory is made. And input gate decides how much of this new candidate memory will influence the final candidate. So it's a little bit similar to what we were talking about for GRUs, but now we are talking everything in terms of candidate memories, or there we were thinking in terms of hidden states. Hidden state will come in the picture, and we will create a hidden state using this output gate. But right now, let's just focus on this candidate memory. So we have a candidate memory at time t-1. Forget gate decides which parts of the candidate memory to forget. And this step, this tanh step calculates a new candidate memory, this intermediate candidate memory. The input gate decides how much of this intermediate candidate memory to use to calculate the final candidate memory. So as you can see, this intermediate candidate memory, after being operated on by the input gate, is then added to the original memory, which was operated on by the forget gate, and that creates the final candidate memory. So this forget gate and input gate basically decide how much of the previous memory to use, how much of the new memory to use. And then this is the final gate, which is the output gate, which is basically exactly the same as we were doing in RNNs. You have a hidden state, you have the input, it passes through a sigmoid, and then the only new thing is we are using the candidate memory, taking a dot product of the intermediary hidden state with respect to the candidate memory, and then creating the hidden state. So this was the whole LSTM architecture. Let's now look at the equations, and they are exactly or more or less the same as what we have been taking a look at so far. So for all these 4 steps, the forget gate, input gate, generating candidate memory, and output gate, it's the same thing. You have an input, which is xt, some weights, a hidden state at t-1, some weights, and some biases. And there are some different activation functions applied. So all of these gates have sigmoid because you want 0 and 1 as output, while CT, which is the candidate memory, has tanh activation. All of these give us the output of forget gate, input gate, and output gate. Then, like I said, you modify the intermediate candidate memory with the input gate, you modify the previous candidate memory with the forget gate, and that gives you the final candidate memory. This candidate memory and the output of the output gate then decide what the hidden state should be. So yeah, so this whole part is basically modifying the candidate memories to decide which one is going to be used, how the new one is calculated, how much of the previous one to use, and then generating the new candidate memory. And then this part is using the newly generated candidate memory and the output of the output gate, deciding what or calculating what the hidden state should be at time t. So in this way, LSTM can also keep a memory. So it can even consider things which it saw much further out or much further back in time, because it can save this memory and then just modify it, whether very small with very small increments or with very large increments, and then decide how much of it to use for each update step or for each hidden step. And another advantage is both GRUs and LSTM sort of solve the problem or reduce the problem of vanishing gradients, because you have this pathway through which backpropagation can occur. And then this is just the final step, which is up till now, we have been only talking about hidden states, and all the RNNs or all the LSTM, everything we said was containing only one layer or one hidden layer. Instead of that, you can actually practically have or need multiple hidden layers. So you will have multiple hidden layers, and each hidden layer will have multiple states at different time steps. And that is what gives us a deep RNN. This is the more practical architecture, which is used in like for any application you'll do. So yeah, that's all I had for the theory. And then we can either take some questions or we can move on to the coding session.
Okay, so can you guys see my screen?
Yep.
Okay. So yep, I know the theory session ran a little bit longer, but it's going to help us here in the coding session, because then I don't have to go through same things again and again. In case you do have questions, please feel free to sort of ask them in the chat, or you can or you can just unmute and ask them. I've also shared the link of this notebook in Slack, in the Slack channel, so feel free to sort of copy it in your own Google Drive and start working on it. Most of the notebook has comments written over it about what we are going to do and how things are going to run. So so you can do it yourself, or you can just look them up to and so on. So this is what we'll be doing. The workflow is written over here. We'll be looking at how to create dictionary and vocabulary. And the vocabulary will be doing some sort of padding to make our life easy. In this particular case, will be one hot encoding our data. We'll make all 3 of the models which Kshitij talked about. So we'll be creating a basic RNN cell, we'll be creating a GRU, we'll be creating an LSTM, and then we'll train one of the models using how PyTorch does it, or how you'll do it in PyTorch, and try to evaluate the model. Now, the D2L book uses the whole HGWell's time machine, but here for illustrative purposes, just make life sort of easy and make it easy to understand for you as well. We're going to just use these 3 sentences over here, which is going to be our data for this session. So it's, hi, how are you? Good, I'm fine, and have a nice day. And the aim would be that we'll be using this in, so we'll be tokenizing this at character level. So we'll be splitting hey as HEY and so on, and then spaces and everything. And then we'll take it from there. So the first step is to actually just find out what all unique characters that we have in this whole of the data set. So I think the simplest way of doing this is one, we just concat all this text. Yep, and then create, and then just do a set on top. So set is a Python predefined function which just gives you all the unique values, and this is going to give you all the unique characters. So let me also run this. That's all the imports which we'll need for this. Okay, so let's see what came up in. So it gave you all these unique characters, list of all the characters which are present in this, which are unique. So it doesn't have all the repeated ones. And now we'll create two dictionaries. One, so what we'll do is we'll mark every character and give it a unique integer, and just create a dictionary which maps an integer to character and then character to integer. This is our very small basic version of, or like a baby version of how to create a dictionary and vocabulary. So to do that, this is again very simple, using just normal Python commands. Okay, so enumerate chars, and that just creates our integer to character, so we can see what it looks like. That's what it did. It gave an index 0 to h, 1 to the space, 2 to r, and so on. And we'll create another dictionary because this is our key, this is our value. We'll create something which goes in the other direction. This is going to help us predict something. So we'll create a dictionary which goes like this. So we want the value as the key now, and key as the value for key, comma, value in char dot, not char dot items, into char. So this should create a dictionary which does the thing, which is sort of opposite to, yep. So here we have, so here one was mapped to space, now space is mapped to 1, and so on. So this is what we'll use in this. So the other thing which we want to do is just to keep things simple. This is our text, and all three of them may or may not have the same length when it comes to characters. So I just want to find out what the maximum length is and just pad the data with a space to make all of them the same length. So you can just do max of a list, and list has len of x for x in text. If you think any step is unclear, please feel free to pause me, and I'll explain what's going on. I love writing one-line for loops, so that's what I'm doing. So what it does is, so you have three items in this dictionary, and it's going to take a length. It's going to create a list which will have just length of each of them, and take a max of that. So the maximum length is 15. And now what we'll do is we'll just pad our data if anything which has length less than 15. So this is something like for I in range len of text, while len of text of I is less than max len. Just pad it with spaces, so text of I plus equal to with a space. So what this will do is it will give you all three sentences in our list will have the same length now. So if you do print text, you can see there's an extra space here. Probably this was the only one which had slightly less number of characters. Now up till now, what we have is these three sentences, and we'll now and as Kshitij was talking about earlier, converting these to or actually wait, the first thing I have to, okay, sorry. So the first thing I'll be doing here is what we want our network to do is we'll give it some part of the sequence, and we'll ask it to predict the rest of it. And I know this is just three sentences over here, but for illustrative purposes, it's probably going to work out. So the way we're going to do it is as follows. So let's do s in text. So it's just going to iterate over text. We'll do input sequence dot append as everything till the last word. And just bear with me for a second and I'll show you what I'm doing. And then target sequence dot and here. So let me just print both of them. So let's print input sequence and then print the output sequence. Oh, target sequence. Okay. Yeah. So what it has done is this is what we'll be inputting. Hey, how are you? And then we are missing and you. And this is what the target should look like. So H will go in first and it should predict E. And then similarly, E should go in next and it should predict Y and so on. So this is what we have done. So we have taken everything except the last character for the input, and for the target, everything except the first one is our target. So this is what we'll be working with. And the next step is to actually now use the tokens which we so we created a dictionary called int to char, and every character over here has the integer associated with it. So we can use this and this one, just char to int to sort of tokenize each and every character in our input. So this input sequence will serve as the input for all of our networks today. So this is what we'll do now. So for I in range text input sequence of I is equal to, so we have to go from char to int, and this is the dictionary, so we are just calling the key over here. Let's see for C in input sequence I, and then we do the same thing for target. So target sequence I is equal to, again, char to int C for C in target sequence I. We can print both input sequence and target sequence to see what it looks like. What this does. Okay. So what we had was, hey, how are you? The review was not complete, and now every character in this has been matched to has been sort of mapped to an integer. This is what this is why we created this char to int. And the next step, and the same thing goes for target sequence. So the next thing which we'll do now is we'll use one hot encoding for this, and we'll one hot encode each and every number over here in the list. Okay, so for that, I have three variables which are predefined. So one is the size of the dictionary, which is literally just length of the char to int dictionary. The sequence length, which is maximum length -1, because these are all 14 character sequences. Because remember, we sort of chopped one over here and then one over here. So this is 14 length one, this is maximum -1. And then batch size, which is 3 in this case, because we just have 3 sentences. So we'll write a function which will sort of convert, which will one hot encode our input sequence. And what we want the output to be is it should have the shape of batch size, comma sequence length, comma one hot encoding size. So what we can do is we can do output as np.zeros, and we can pre-create an array with zeros and then fill one as per the index over here. So we create zeros with batch size as the input. So batch size, and then sequence length, and then finally the dictionary size, which is the size of our one hot encoding. And then we're just going to set d type to float 32, because that's what we'll be using with the neural network, with our neural network later. And then for batch in range batch size, Then for sequence in range, sequence length. Now output batch, comma sequence, comma. So now we'll take, so our input sequence, which is it's called a sequence over here, is a list of lists. I copied the Slack message over here. Anyway, output and batch sequence sequence, and then this is, so yeah, here we have sequence. Now this is a list of lists with the first where the first index is batch and then the other one is sequence, and we set this to 1. So everything else is going to stay 0. And in this 3-dimensional thing, what we'll do is for each batch, for example, like for this particular case, and then for each sequence in that, we'll go to sequence, which is this, and then batch, which is, let's say 1 over here, so it will go to this one, and then sequence, which is whichever sequence it is, and just set that particular value to 1. And that's it. That will one hot encode our return output. That will one hot encode. I'll show you how this looks. And see this and this. So this is what the shape is. 3 is the batch size, or it's also the number of sentences which we have. 14 is the sequence length, because this is what we are training. This is what we are training with. And 17 is the one hot encoding size. This is that we have 17 unique characters. This is what we started with. So if you do output, it's going to be a huge array, just a lot of zeros and few ones here. It's called input sequence. So here's what we have. So it's, the first one is 1 over here. The second one has 1 somewhere. Okay, wait. Yeah, the second one has 1 somewhere over here, and it's just one hot encoding 0, 4, and so on. So that's what we have. So we now have all of our data in some format which we can feed to our neural networks, and that's what we'll be doing. So one thing which we can do right now is this. So input, see, just make it a torch tensor. So do a torch.from numpy sequence. So now it's a torch.tensor. Similarly, we can do target sequence is equal to torch. It's an array. It's not a numpy array. It's just a list. So we'll just do torch.tensor target sequence. So now everything is a torch tensor instead of having numpy array or lists, which sort of unifies everything that we have to do. One thing which I wanted to note is that we did not one hot encode our target sequence. We only one hot encoded our input sequence, and that's that was something which was initially puzzling to me. I've been coding in TensorFlow most of the time, but recently started working with PyTorch, and with TensorFlow, you have to one hot encode both of them. With PyTorch, the target can just be a number, for example, this thing 4310 and so on, and it will automatically take care of it. So that's something nice. It's nice to know as well. So now we'll keep all of this aside for a while, and we'll start coding our basic architectures. We'll code our basic RNN cell, and we'll try to just pass some data to it and see if it actually works or not. We'll do the same thing with GRUs. So here are all the equations already written up, and then same thing goes for LSTM. So this is what we'll be doing now. We'll be coding all these networks, and this is where sort of our session 1 comes in, and this is what Kshitij was also talking about initially. So what we have to do is we have to create networks which have weights WXH, WHH, and then WHQ, and then these are 2 biases. But if you remove this particular one from the middle, this is exactly a multi-layer perceptron. So this is the concept which we'll be using for creating all 3 of these networks over here. That and if you just look at this one, this can also be represented by a multi-layer perceptron without a bias. So that's what we'll be using. This is again a multi-layer perceptron without any activation function in it. So that's how we'll start coding this. Any PyTorch neural network, the way, if you are doing it in a functional sense, is this. So you will define a class and you inherit something called rnn.module, and then you do something like super basic RNN, and after that you do self and just init it. So this is for inheritance. You can look it up if you don't know what inheritance is, but this is just to sort of kind of initiate this rnn.module in a certain way. So now we'll define our weights here. So the first one is wxh, and we'll define that. We'll have self.whh, and then we'll also have self.whq. So these are the three things which we need to define in this. The other thing which we need for our network is a forward. Is a forward function, just self comma. So we'll call it input x and hidden, because remember there are two things. Or let's call it old hidden state. So there are two things which go as an input to your RNN. One is your input at a particular time t, and then a previous hidden state, and that's what we use over here. So these are the two things which we need. So let's start coding this. So this is nn.linear with input. So this is wxh. So this has to map your number of inputs to number of hidden, to number of the number of elements in the hidden state. So your in features is num inputs, and out features are num hidden. And we will set bias to be true in this case. So what we have just coded right now is this term wxt. So it's going to have it's xt times wxh and then bh over here. The next one is so next one is ht minus 1. So it maps the previous hidden state to it takes the previous hidden states and then multiplied with whh, which is, so it's going to have same number of in and out features, which is equal to number of hidden states. So its in feature is equal to num hidden, its out features is equal to num hidden, and then we'll set bias is equal to false in this case. And that's, so these two combined will give us this particular function over here. And the last one, again, nn.linear. So in features in this case is num hidden, because it's taking the hidden state as the input. So we are coding whq. So we are taking hidden state as the input, and it has to go to the output. In our case, input and output are of the same dimension, and that's why I didn't add another sort of variable here, which is num outputs. But if you are working with something which has a different length of output, you can add that and change the number here. In this case, in our case, it's very simple. So it's just inputs. And then we do need the bias in this case. So check there's a BQ over here. So that's what we have. So the forward in this case is very simple. So the first thing we need to create is a new hidden state. A new hidden state is given by, so this phi is the nonlinear activation function. We'll take torch.sigmoid for this. So torch.sigmoid, and it has these arguments. So the first one is input and wxh. So we'll have self.
Yep. Typo num hidden in the whh.
I see. Thanks.
Thanks for pointing it out, Ramesh.
Okay. So this is self.wxh, and then it will take the input x. plus, so this already had a bias in it. So this term, and this term is accounted for. Now we'll take care of this term, which is self dot WHH, and which will take the old hidden state. So this gives us h of t. The other one is the output. There's no activation over here, so all you have to do is self dot WHQ, and the input to this is just the hidden state, and what you return is output comma hidden. So this is our very basic RNN cell. It takes in so it has 3 weights: WHQ, WXH, WHH, and WHQ. All of these are taken care by using NN.linear, which is just a fully connected layer. And then we map everything to every other thing using these two equations. So you have hidden state, which is given by a combination of inputs along with some weights, and then previous hidden states and the bias. So that's why we had bias true here, takes care of that. And using that hidden state, whatever you've computed, we compute the new output, which has its own set of weights and bias, which is given by WHQ. That's why again the bias is true over here. And then what you return in the end is output and hidden. So that's what we have for our for this particular thing. Our number of inputs is given by the dictionary size, because we have one hot encoded our data. We're choosing number of hidden elements to be 8. This can be any number. You can choose it to be 2, 3, or 500, 600, whatever you like. We're choosing 8 here, but you can choose anything. There's no special reason why we chose 8. All right. So now this is our model, which runs. You can print this net if you want to. It's not going to give you anything. Oh, no, it's not called net. It's called model. So it's going to give you something. All right. So it has 17 features as input for the first one. So this is WXH. And it maps to 8 hidden features. WHH takes the old 8 values from the old hidden state and maps it and then multiplies it with WHH, which is 8 by 8 matrix. Then you have WHQ, which maps from 8 to 17. So that's what we have over here. We now initiate our hidden state. So our hidden state is so let's go ahead. Initial hidden is just store zeros, and this is going to be of the shape 3 and 14 and 8, and I'll come to this in a second. Just wait. And then D type is torch dot float 32. So ZDR OS. All right. So we just have zeros over here, and now we can feed in something over in this case our input sequence and get some output. So we'll have output comma hidden is equal to model, and the two things which will go inside this is input sequence. This is what our input is, and then the initial hidden state. Okay, it has no attribute WH. Oops.
I think it's in the forward function.
Oh, I see. It's WHH. Yep. Thanks for pointing that out. So you take that, you initiate the model again. And now we run this. Yep, now it runs. So I can see we have output.shape, and you can, for some reason it's running really slow. I can type much faster than this, and it appears much later. Yep. So this is what we had input. This is what our input shape was also earlier. So 3, 14, 14, 17. The 17 is because we have one hot encoded everything. 14 is because that's the length of our sequence, and 3 is our batch size, or the 3 sentences which we have. And then it gave us something for each one of them. Right now, even if I'm not gonna do it, but just gonna show you. So just gives you some numbers because again, we didn't train anything. It just randomly initialized some weights and multiplied whatever numbers we gave it to something and just gave us some output. But what you can do is you can actually go ahead and take this RNN cell and try to train it. This is one RNN cell. What you have to do is put in a sequence. So while call with the set with this cell number 30, you can keep calling it again and again, except now instead of initial hidden state, you can now give a new hidden state which came from the previous and so on. So that's why we output both the output and hidden. You can use that as an input for the next step and so on. So this is what a very simple basic RNN cell looks like. Okay, so we'll now move ahead. We'll now create the gated recurrent unit, or GRU cell, and this is extremely simple once you actually know what we are doing here. So it's the same thing for all these W's. We'll create a NN.linear or a dense layer, and we'll just use that in the forward function at the end to map what goes where. So we have WXR, WHR, and then for one of them we'll just set bias to true. For one of them we'll set bias to false, and that's gonna be it. So again, it's a PyTorch functional model. So we start with super basic GRU and self, and then just initiate it. And then we'll do self.wxr. This will be something. We'll have self.whr. This will be something. We'll have self.wxz, self.whz, and then there's this candidate hidden state. So we'll need xh for this, self.wxh. We need self.whh for this, and then that's it. We'll need one for the output as well, because you use this hidden state too. So what did I call it last time? Yeah, it's called HQ, but let's just call it self.o for now. Okay. So this one starts with NN.linear. We'll again match number of inputs to num hidden. So this takes in the input and maps it to hidden. We'll set bias is equal to true. And the next one maps the old hidden. So it maps from the old hidden layer. So it's gonna have same num hidden as input, as in features and out features. So it's num hidden to num hidden. And then bias is false because we have set the bias in the first one. So this takes care of the first thing. Let me also define the, sorry. Forward self input x will do old and state here. So this is the old hidden state, and what else do we need in this case? I think that's all we need for the input. Yep, that's all we need for the input. So the first thing is R r at time t. So this is given as torch dot sigmoid, and it takes self dot w xr, and the input is input x plus self dot whr, which has the old hidden state as the input. So that's our first RT. The second one is very similar. It's more or less the same equation. So what we can do is we can copy these two and just rename this as xz and hz. And now we can again copy this and call it z of t with the new xz and hz. So these two take care of these two. Now we have tan h, and this tan h needs all of these things. But again, see, the first term is very similar to these ones over here. So it's just the first, it's going to stay the same. The second one, the input changes, but the other one, it still has the same. It still has the same dimensions of WHZ or WHR. It's just taking an element-wise product of RT and H of T minus 1. So it's again gonna be this again. So no changes over there. And finally, we'll be using this HT to map it to our output. This is the same equation which we had. So this is the same equation which we'll be using over here to get the output. It's not written up over here, but it's which goes from num hidden to num inputs, and we need a bias in there. Now let's make the candidate hidden state. So we'll just call it h tilde. It's torch dot tan h, and now the inputs it takes is self dot wxh with the input x, plus there's a element wise product, so we use torch dot mul for this. So this is element wise product of two of other vectors or actually tensors in this case. So we need r of t, r at time t, and then the old hidden state here. So that's old hidden state. So this gives us this particular thing over here, and then this is multiplied by WHH. So this goes as the argument of self dot WHH, and yep. So this creates a candidate hidden state, and now we create our hidden state as follows. So this is torch dot again element wise multiplication. So this is z of t with h of t minus 1. So that's old hidden state, plus torch again element wise product of 1 minus z of t with the candidate hidden state. So that's h tilde. And now what we did, okay, need the output as well. So the output again is going to be self dot out the hidden. So you return the output and hidden. So it's very similar in construction when it comes to the GRU. We can do the same thing over here. Actually, we can copy and paste the same things. So instead of basic RNN, we'll just change this to a basic GRU. So that's it. We can again run this model with the same inputs. We already have defined all the input sequences in the hidden states. So we'll use the same thing. Again, these are randomly initialized things. So once we it's E over here. Okay. So now again, since everything is randomly initialized and we didn't train anything, it's going to give us some random numbers, but the shapes should still stay the same. Yep. And if you print it, again, so it just computes something for you. Again, you can, whatever training loop you will write to train the basic RNN unit, you can use the same loop over here, just use this newer GRU. Sorry, this is RNN, this is GRU. Yep, use this instead. And you can do everything in the exact same fashion and move ahead. Okay, so next is the LSTM, which if you see has exact same or very, very similar structure. You will do the same exact thing where you define IT, FT, OT, candidate memory, candidate memory in the candidate memory, which is intermediate in this case, and then the final one. The major difference between LSTM and all and the above two is that these had only two inputs, which is your input and your old hidden state. Now you have another input in this case, which is just your candidate memory. So it's the same thing over here, and I'll start copy pasting most of the stuff because actually okay, so instead of basic GRU, this now becomes basic. This, so now we have, so we copy this. I'm gonna need this bit again and again. So the first one is WXI and WHI. And then the next one, so this is for IT. The next one is XF and HF. So that's for the forget gates, HF. The other one is, so this is for the output. So that's port XO and HO. And then we need something for the candidate memory. So that's XC and HC. So there's that, and that's pretty much it. This is what we need in here. So now we'll write our forward function. So this is input X old hidden state and old let's just call it old memory. So the first thing is I of t, which is dot sigmoid of self dot wxi with input x plus self dot whi with old hidden state. So that's part one. Next one is ft, which takes in which takes in xf and hf. So we change this. The next one is, so we just replace all the f's with o's. So that's ot, this xo, o, and then we'll create c tilde now. Just dodge dot 10h, and it uses dot with the input x plus self dot, oh sorry, what am I doing? This is w, self dot w at c with the old hidden state, and then we create c of t, which is the element wise product of ft and the old memory, and oh wait. Yep, so that's correct. And then again torch dot, so again torch dot with it and c tilde. That is that. And now the hidden state is now given by an element wise product of OT and torch dot tan h times CT. And what we return is, so let's see, is the output gate and blah, blah, blah. Yep, so we need this, the output. So we need the hidden and then the memory is CT. So you can do the same thing. I'm not going to initiate this and sort of do the same exercise over here again. See, we have, I guess, less than sort of 15 minutes, but this is how you code up the whole LSTM. As you can see, very similar and very easy. Just need to have all the equations in one place, and that's going to be it for you. For next couple of minutes, what I'm going to do is I'm actually not going to even code this. I'm directly going to show you the code for the PyTorch RNN implementation and see how you actually do this. So just give me a second.
Just quickly before that, I think the LSTM thing should also return output, right? There should be
yeah,
output there, and
yeah,
then
it should also have an output,
like it was
because
done for GRU and RNN.
Yeah. So it will also have one more thing in it. Yeah. Okay. So just give me a second. Let me pull up that code. So, yeah. So this is how you would sort of do RNN, a very simple RNN, and the code more or less stays the same for LSTM and GRU as well. What you now do is you do self.rnn is equal to nn.rnn. And here you can have an input size, hidden layer dimension, and n layers. So remember, Kshitij was at the end talking about deep recurrent neural networks. That's when you have multiple layers of it. And that's what you can do. You can directly just define the number of layers in this, and torch.rnn, this torch.nn.rnn will take care of everything. This is the last one, self.fc, which takes in from your hidden dimension to output size. This is the same thing as this over here. What you get from your RNN is this hidden state, and then you just learn these weights and biases to give you a final output as well. So this is how you create an RNN. This similarly nn.lstm, nn.gru, it gives you very similar things. The forward in this case is written in a slightly different fashion. And that's sort of because I was writing it for this particular case. So in this case, the forward didn't take any hidden layer, the hidden output. And since we are passing the whole thing at once, I was initiating the hidden state within the forward loop itself. So you take this, you give it your input and your hidden, it gives you an output, compare it, you just reshape it, and your output is given by this final layer. And the initialization of hidden layer is just zeros. Just now remember that it has number of layers in it as well, because you'll have to initiate your hidden state for each layer separately. Now it's more or less the same thing which we have been doing. You define your model, you define number of epochs you want to train it for, get a learning rate, and we use cross entropy loss because our loss is one hot encoded, and we use Adam for our optimizer. And the training loop, I'm also just going to copy paste that here. It's going to look very similar to what we have. Let me see if I can actually run this. It should run. Yep. So the training loop is also very similar to what we have been doing in PyTorch so far. Okay. Yeah, so here's the thing. You zero grad your optimizer, you give in your model with some input sequence, you get your output and your hidden. You compare this output with your target sequence, again, just reshape it, do loss dot backward, optimizer dot step, and in this case, it's just printing loss at every 10th step. Since we only had 3 sentences, very small vocabulary, it just runs even on a CPU very quickly. And then I have 2 more functions written up over here. What they do is you can either predict what the next character should be, or you can ask it to predict for n number of sort of characters, and I'll show you. So if you do here, predict model, and then you give it a character, let's say give it h. What it does is it again calls your char to int, one hot encodes it, and then gives it to your model and asks, hey, what the next thing should be. Then applies a softmax on it, and then takes the max and goes and does the int to char thing. It also returns you the hidden state just for you to see. So if you predict h, okay, wait. So if you ask it to predict h, it gives you e. If you give it he, it gives you y. It's very simple over here. So now let's do sample, give our model over here, and ask it to give, let's say, the 15 characters, and we'll give it hey as the input. So it's gonna take hey, and then it's gonna give hey, how are you? And given we just had very small data set, it has probably overfitted and learned everything we've sort of trained it with. So this is what I have for you today.